Hello, I am Grigore Rosu. I'm the founder and CEO of Pi². And our mission at Pi² is to bring all programming languages and the next million of developers to Web3. It is well accepted and broadly acknowledged and proved over and over again in surveys that fragmentation is one of the main critical pain points in Web3. Fragmentation of ecosystems, blockchains providing different languages, different applications, fighting with each other for the users, to steal users from each other. Liquidity, billions of dollars spread all over, and the user experience is terrible. Everybody wants to fix it. Let me tell you how we want to approach, how to solve this problem of fragmentation. Through universality. Universality at three different levels. First, universality in programming languages and program execution. We firmly believe that all programming languages should be available to Web3 developers. Universality with respect to verifiability and proof mechanism. Verifiability should not be negotiable. Every execution should be provably verifiable. And we should also allow different proof mechanisms. We should not be stuck with just some of them. Also, universality with respect to distributed consensus protocols that assure security. We should be able to achieve consensus at the speed of light for applications that operate that way. How precisely we do that? So we offer a universality stack containing three components: the universal language machine, the universal settlement layer, and the universal consensus protocol. The universal language machine is a blockchain architecture that allows you to write smart contracts in any programming language, existing programming languages or new programming languages, even in programming languages that have not been invented yet. You can even bring your own language, BYOL. Plug and play your language into the blockchain and then write smart contracts in the language. ULM builds on top of the USL, the Universal Settlement Layer, which allows you to generate proofs of execution for any programming languages, executions with any programs in any programming languages, therefore proofs also across different ecosystems based on different languages. And also it is fast and low latency settlement. And when we talk about proofs in this presentation, we mean two types of proofs, both mathematical proofs and zero-knowledge proofs. Usually, in the blockchain space, we understand zero-knowledge proofs by proofs, but you'll see that mathematical proofs are even more important when it gets to actual correctness. And the USL, to achieve all these performance benefits, builds on top of the Universal Consensus Protocol, which is a consensus protocol for claims that are true, and it is not based on or relies on a total order of transactions. It is a set consensus protocol. You achieve consensus on a set of truths. And this can be done, amazingly, at the speed of light. Literally, all you need is a round-trip message between the client and the verifier to get confirmation that this claim is true and to achieve agreement on that. All right, so what does this really mean? Well, it means the following, that through ULM, we can now bring all the developers in the world to Web3. They can use their favorite programming languages. They no longer have to learn obscure programming languages in order to be part of the Web3 space. That includes millions of developers out there, tens of millions of developers, not to count all the AI agents who are also programmers themselves. USL, what it really means is that we can settle correct executions on this common layer across Web3, Web2, all kinds of applications. Any computation that has nothing to hide, that wants to prove that it happened correctly, can settle on the USL. Web2 or Web3. Everything, everybody, any computation can settle. AI agents can settle their inferences. And UCP means that we no longer have to wait seconds for finality. It will happen at the speed of light. I don't need to tell you how important that is and what opportunities this brings. Basically, any developer in any language can now participate in the Web3 space. We no longer have to go with only 20, 30,000 programmers like today. We can very quickly extend to 20, 30 million developers, not to mention all the AI prompt engineers. Programs in the future will be written by AI agents, not by humans. And all those will participate as well in the Web3. All right, so enough talk about universality in general. Let's now go deeper and try to understand why we need universality. Actually, instead of why, actually that's not the right question, why universality. The right question is, why don't we have it yet? Because you want universality. I hope I convinced you that we want all that universality to eliminate fragmentation or reduce fragmentation. Why we don't have it? Well, programming languages come into the picture here. This slide shows the state of the art in the programming language field. It's a lot of pain, what this slide shows. Basically, every single programming language combined with any single tool is an arrow in this picture, and that means a whole complex system by itself. For example, C and compilers. We have GCC, ICC, Clang, tens of years of effort, hundreds of many years of effort. Or Java interpreters, or EVM interpreters like Get, Rest. So all of these tools need to be developed and need to be maintained. You cannot just add a language to an ecosystem. You need to bring all the tools so developers can develop actual programs properly using the language. So maintenance is a hell, training developers is hard, and tools are always behind 2 or 3 versions of the actual language. So bringing a new language to a blockchain, or anything for that matter, is a big deal. And this is what we believe is a major barrier, a major obstacle that we have to avoid. Well, how can we do that? How can we avoid that? And this is what we believe is the key to avoid all this fragmentation of programming languages and eliminate the barriers brought by programming languages. This is not a new idea. I proposed the K framework back in 2003 when I started my career as a professor at the University of Illinois. And I built it with my research lab, my students. Then several companies adopted it, several other universities adopted it to teach programming languages. But this is the idea. Actually, let me tell you what I don't think is the right way to go. Picking one particular language, no matter how beautiful the language is, and no matter whether that language is high level or low level, LLVM, any language that you think this is the best language ever. And by the way, I mentioned LLVM because it was invented in our department at the University of Illinois, so I can mention it. So pick LLVM, no matter how beautiful the language is, it will never be the ultimate programming language. Right? So if you compile translate any other programming language to that one language, you'll suffer from the same problems like before. You'll have compilers that you have to keep updating, you'll have each tool that needs to be updated, and you'll have errors, and so on and so forth. So we believe that the solution is to actually do the exact opposite, which is what I proposed back in 2003. So instead of translating everything to one language and call it the ultimate language, instead of that, what we do, we define everything mathematically. Every single programming language is a mathematical theory called a formal semantics. Let me ask you a question here. How many of you here knew, and be honest, that in order to talk about correctness, somebody gives you a program and says this program is correct. So in order to even talk about correctness, you need a formal semantics of the programming language. How many people here knew that? Nobody? Okay, you see? So that's what happens. People talk about correctness all the time, but in order to have correctness, you need a formal semantic, which is a mathematical definition of the programming language. Once you have that, a universal language framework, like the K framework, will generate for you all the tools that you need from that mathematical definition, including an interpreter. Okay? So you don't have to implement an interpreter by hand. You don't have to implement a compiler by hand. You don't have to implement a program verifier by hand anymore. All right? All of them are generated from the actual mathematical definition of the language, and they are correct by construction. What that means is that everything they do, including the interpreter, which executes a program, everything they do is done using a mathematical proof under the hood. Okay, so you can take that mathematical proof and check it, and now you know with absolute certainty. Forget zero-knowledge proofs. There's not absolute certainty. But this is absolute certainty that the execution happened correctly, because a mathematical proof was constructed, and that mathematical proof was checked. All right? So that's the magic of a universal language framework. Any programming language in the framework is a mathematical ground truth, a set of axioms, and now everything that you do in terms of execution, verification, everything you do with that programming language becomes a rigorous mathematical proof that can be checked. So this is the key that allows us to get universality, because there is nothing specific to any particular programming language here. And you may say that, yeah, that's great, but it must be horrible to define a language mathematically. And I can tell you that no, far from it. It is actually easier. And you don't have to trust my word. Just look at this slide. It is easier to define a formal semantics of a programming language than to implement an interpreter for that programming language in some ad hoc programming language. What you see here is a complete language definition of a simple programming language, but what is important is that it's complete. On the left, you have the syntax. You can see the if-then-else statement, for example, here in the middle. To the right, you have the semantics. All right, the if-then-else, notice that it's strict in the first argument. You have to write strict in the first argument. That means that it evaluates the first argument. And then in the right side, where you have the semantics, the actual axioms defining the language, we have two different rules. One when the first argument is 0, one when it is not 0. Exactly what you would expect. I claim that this is much easier to read than an actual interpreter for the language. But the beauty of this is that this is very rigorous, mathematically very rigorous. And yesterday, on the same stage here, we demonstrated how ULM works and how smart contracts written in this language actually execute. All right, so now what is pi squared? Pi squared comes from proof of proof, specifically from zero-knowledge proof of mathematical proof. Okay, remember that in K, when you execute any program in any programming language, you get a mathematical proof under the hood, right? Wonderful. The problem is that that mathematical proof can be big, and it is big, so big that you may not even be able to store it. So the secret is to actually discard it as it is generated, you check it, and you generate a zero-knowledge proof of its existence. And this is where the name pi squared comes from. Zero-knowledge proof of mathematical proof. All right, this slide shows the big picture, which we call verifiable computing 2.0. Why? Because this is verifiable computing as we know it, but universal. It works with all programming languages. It is correct by construction. No ZKVM to be formally verified. All right, this is how it works. Let's start with the output. At the output, we get a zero-knowledge proof. Same like in any other ZK circuit. At the beginning, you get as input a program and an execution environment. Don't look at this yet. Which is exactly what you get in any ZK VM, which is specialized to this particular programming language in which the program is written. What is different here is that the programming language itself is an input. All right, and then K does its magic and generates a mathematical proof from the execution of the program. Right? So now I don't have to trust any of these complicated stuff because I verify the mathematical proof. Once I verify the mathematical proof, I know that the execution was correct with absolute certainty. How can we do that? Well, we can do it using ZK technology. So now we completely separated concerns, computation from cryptography. Computation is verified with the best that we know after more than 50 years of research in programming language semantics and formal semantics in general. Now we are done with this part, and now we can focus on just one aspect. Let's generate a ZK proof for mathematical proofs. This builds on everything we've learned in probably in the oldest field of computer science, programming languages. And it is not only universal, that it works with all programming languages, but it is correct by construction. There is nothing to formally verify here. And formal verification is my field. That's what I've done all my career. Now, finally, we don't need it. All right, and this is my last slide. Let me tell you what the current status is. We are a new company. We started 1 year ago, exactly 1 year ago, at ETHDenver 24. And this is what we really wanted to do back then. First of all, no matter how many times I said correctness is critical, in the end, everything boiled down to performance. Everybody asked me, yeah, but this is going to be slow. Great, it will be correct, everything correct by construction, but it will going to be slow. Not anymore. So we had to improve the performance of K by 10x, to make it 10x faster, in order to be convincing. And now it is actually 15 times faster than it used to be after 1 year of effort. Now it's 1.58 faster than GET. Okay? Please, if there is one thing to go home with, this is the most important thing. You execute a program generating a mathematical proof using a prover, and you get a proof of correctness for the execution of the program using the most rigorous known framework for correctness that we humans know. And that happens faster than an ad hoc manually written interpreter, which is the most used client in blockchain. Okay, so this is fascinating, for me at least. It's the first time that happened. So formal semantics, whoever tells you that formal semantics is great but it's slow, tell them not anymore and send them to this. By the way, all these papers confirm and explain how it happens. So this paper explains all the engineering that has been put into this, how to make it really, really fast. The second thing we wanted to demonstrate was that proof of proof makes sense as a concept, that we can indeed generate zero-knowledge proofs of mathematical proofs. And we plan to do it with just one ZK VM with risk zero. But what happened was that once we started getting results, we were approached by other friends, different other ZK with other ZK VMs, and before we knew it, we ended up putting together a benchmark, which now is the largest benchmark for ZK VMs that we are aware of. Has almost 10,000 programs, more than 1,200 programs, but multiplied by 7, because now we run them with 7 different ZK VMs. And yeah, so it's all open source. If you have a ZK VM, please try it and add the 8 or the 9th or more. So the bottom line is that now, because of what I showed you previously on the previous slide, we can bring all programming languages to all ZK VMs. Okay? You no longer have a ZK VM for RISC-V or for EVM. No, now you have a ZK VM for all programming languages without any compiler to your language. And finally, we wanted to show that we can indeed settle on the USL claims corresponding to blocks on Ethereum, and we've done a lot more, actually. We managed to integrate with Wormhole. So USL now provides an alternative to the Guardians on Wormhole, which we all know they are a big pain. They run full nodes on all the networks. So now you can settle everything they do on the USL, actually. And one other thing that happened last year is that ULM, the blockchain architecture that supports all programming languages, plug-and-play your language, now is actually alive. It's not a blockchain, it's still in our lab, but it's a proof of concept showing that, yes, you can plug and play your programming languages, and then write smart contracts in them, and then you have interoperable programming languages. So interoperable programming languages, interchain applications, everything going through mathematics and mathematical axioms, and 12 mathematical proof rules that can prove anything about any theorem about any mathematical theory. So, all right, with that, And by the way, all this demonstrating USL and ULM, has been recorded. They are on YouTube, on our webpage. Please try them out. Watch them first and then try them out. And with this, I'd like to invite you at our booth as well for a tour right next to the coffee place and see a live demo of USL and ULM. Thank you.